In this lesson, we will determine whether some series converge or diverge using the integral test, and we will also use an integral to estimate the error made when we use a finite sum to estimate an infinite sum. So first, recall that the integral test states that you have a function f which is continuous, positive, and decreasing on an interval from 1 to infinity. And the nth term of your sequence is given by plugging n into your function. And then it tells you that the integral test tells you that the series from n equals 1 to infinity of a sub n is convergent if and only if the improper integral is convergent. So what that means is that if your integral from 1 to infinity converges, so does your series. And if your integral from 1 to infinity diverges, so does your series. Also, just note, it's okay if your integral begins at a value, or your series begins at a value other than 1, like 2 or 3 or 4. Also, it's alright if your function isn't always decreasing, but is ultimately decreasing, so there's some number past which the function decreases indefinitely. Now let's confirm that the integral test can be applied to the series sum from n equals 1 to infinity of e to the 1 over n squared. And then let's use the test to determine whether this series converges or diverges. So first of all, you have to let f of x equal e to the 1 over x squared. And just note that f is continuous. It's also positive. The continuous part is true as long as x is not 0, but since we care about the interval from 1 to infinity, that's all that matters. So on the interval from 1 to infinity. And now to check that f is decreasing, we take the derivative, and you get that f prime of x is equal to negative e to the 1 over x multiplied by 1 plus 2x over x to the 4th. That's after using the quotient rule and doing some simplification, but this is the derivative, and we have that f prime is less than 0 as long as x is bigger than negative 1/2 actually, so we know that f is decreasing on 1 to infinity. So now let's apply the integral test. And we're going to find the integral from 1 to infinity, e to the 1 over x squared dx. Same thing as the limit as some b goes to infinity, the integral from 1 to b, e to the 1 over x squared dx. Now an antiderivative of e to the 1 over x squared is going to be negative e to the 1 over x. If you need to work out those details on your own, do a substitution for 1 over x. The du would be negative 1 over x squared dx. So that's where the negative comes from. And this will be evaluated from 1 to b. So we have the limit as b goes to infinity, negative e to the 1 over b plus e to the 1. And as b goes to infinity, this 1 over b goes to 0. So we will have negative e to the 0 plus e, which is the same thing as negative 1 plus e. And since e is about 2.71, this is about 1.71. And because this is a finite number, that means that our infinite integral converges. And so by the integral test, your series, n equals 1 to infinity, e to the 1 over n squared, also converges. Confirm that the integral test can be applied to the series sum from n equals 1 to infinity of n over n to the fourth plus 1. So let f of x equal x over x to the fourth plus 1. And this is continuous. This is actually continuous for all x because that denominator is never 0. Also positive. Positive as long as x is bigger than 0. The denominator is always positive. The numerator would be negative if x were negative, but we only care about 1 to infinity, so we have positive. Now the derivative, so we're checking for decreasing now. And if you do the quotient rule and simplify, you get that the derivative is equal to negative quantity 3x to the fourth minus 1 over x to the fourth plus 1 squared. And this is certainly negative so long as x is bigger than 1. So we know that f is decreasing on the interval from 1 to infinity. So now we apply the integral test and find the integral from 1 to infinity of 1 of x over x to the fourth plus 1 dx. So same thing as the limit as b goes to infinity, the integral from 1 to b, x over, now this is a semi-tricky substitution, but x to the fourth is the same thing as x squared squared. And now this is of the form arctangent of something. If you do a substitution for the x squared, you would get that. So if we let u equal x squared, we would get du equals 2x dx. So dividing the 2 over, we'll have a 1/2 in front. So same thing as the limit as b goes to infinity of 1/2 arctan of x squared evaluated from 1 to b. So we have the limit as b goes to infinity, 1/2 arctan b squared minus 1/2 arctan 1. And remember, as b goes to infinity, arctan ends up approaching pi over 2, so we'll have 1/2 times pi over 2 minus 1/2. Arctan of 1 is pi quarters. So that's pi quarters minus pi eighths, which will be pi eighths. So thus our integral converges, and by the integral test, the series also converges. In this section, it is pretty useful to be able to do integrals quickly in your head and do simple substitutions in your head. If you have to work out the details on your own, it's fine. Just integrate on the side and then skip ahead and put in the antiderivative that you find. Alright, let's confirm the integral test applies to this function. So this series is a little bit different because it begins at 2. And one reason it has to start at 2 is if it had begun at 1, you would have had an ln of 1 in the denominator, and an ln of 1 is 0. Your first term would have been undefined. So f of x, we'll define f of x as 1 over x times ln of x squared. And this is continuous and positive so long as x is bigger than or equal to 2. We're all good. This is not continuous at x equals 1, as I said earlier, because the denominator would be 0. Now to test for decreasing, f prime of x is equal to negative ln x minus 2 over x squared times ln x to the third, same thing as negative 1 times ln x plus 2 all over x squared times ln x cubed. And this is also negative, for certainly with x is bigger than or equal to 2, maybe even for values lower than 2, but for all that we care about is 2. So let's apply the integral test. So we'll find the integral from 2 to infinity, 1 over x ln x squared dx. So that's equal to the limit as some b goes to infinity, integral from 2 to b, 1 over x ln x squared dx. So if you work the integral out on your own on the side, you do a quick little substitution for u equals ln x, and you're going to end up with the integral of u to the negative 2 du. So once we integrate the u to the negative 2, we have the limit as b goes to infinity. The antiderivative of 1 over x times ln x squared will be negative 1 over ln of x, evaluated from 2 to b. So that's the limit as b goes to infinity of negative 1 over ln x, ln b, plus 1 over ln 2, and as b goes to infinity, ln b also goes to infinity, so 1 over ln b goes to 0. So this approaches 1 over ln 2, and thus our integral converges. So by the integral test, the sum also converges. Alright, next we have a series that is just written out as a list of numbers, and it's your job to determine the pattern. So this first term is 1 over 1 plus a third plus a fifth, so we have all these odd denominators. So let's start our sum at 1 and go to infinity. So this 1 could be thought of as 2 times 1 minus 1. 3 is 2 times 2 minus 1. So that ends up being 2n minus 1. And the best way to do these is just to guess at what you think might be the pattern and modify it to see what works and then check it. So when you plug in 1, we get 2 minus 1 is 1, which is my first denominator. When you plug in 2, you get 2 times 2 is 4. 4 minus 1 gives 3, which is the next denominator. And then 3, 2 times 3 is 6, minus 1 gives you 5, that's the following one. So let's let f of x equal 1 over 2x minus 1. F is continuous and positive on the interval from 1 to infinity. There is a discontinuity in f at 1/2, but that's not in this interval. And then to test for decreasing, f prime of x is equal to negative 2 over 2x minus 1 squared, and that's negative all the time, so f is definitely decreasing. So let's apply the integral test. We'll find the integral from 1 to infinity of 1 over 2x minus 1 dx. So that's the same as the limit as b goes to infinity, integral 1 to b, 1 over 2x minus 1 dx. So the antiderivative of 1 over 2x minus 1 is ln absolute value 2x minus 1, with a coefficient of 1/2. So that will give us a limit as b goes to infinity of 1/2 ln absolute value 2b minus 1 minus 1/2 ln of 1. And because ln of 2b minus 1 goes to infinity, this approaches infinity, and thus our integral diverges, and so does the series. So by the integral test, the sum from n equals 1 to infinity, 1 over 2n minus 1 diverges. Also recall that we could test for convergence of p-series without having to actually apply the integral test. So for this particular sum, I can rewrite this as a sum from n equals 1 to infinity of 1 over n to the 1.4 plus 3 over n to the 1.2. And both of these, I can now sum the two series individually, so sum from n equals 1 to infinity, 1 over n to the 1.4, plus the sum from n equals 1 to infinity, 3 over n to the 1.2. Now if either one of those series diverge, then the whole series diverges. But in both cases, this one is the first one is a p-series with p equal to 1.4, which is bigger than 1, so it converges. The second one is a p-series with p equal to 1.2, which is greater than 1. It also converges. So thus, your whole series converges. Because it's the sum of two convergent p-series. So next, let's suppose we know that a series is convergent and we want to estimate the sum from n equals 1 to infinity of some a sub n with a sum from n equals 1 up to some capital N a sub n. Like, so you could sum from starting at 1 up to 1,000 or 10,000 or 100,000 or 1,000,000, and we would like to figure out how accurate that estimate is. So let's start by defining the remainder. So this r sub n, that's equal to the total sum, so the value of this expression, if you could find it exactly, minus s sub n, where s sub n is the nth partial sum. And so s adds up all the terms 1 to infinity, s sub n adds them up until n only. So when you subtract these two, you're going to end up with a sub n plus 1 plus a sub n plus 2 plus etc. all the way forever and ever. So if you, say, had found the remainder of stopping at, say, 100, you'd have the 101st term plus the 102nd. That's what's left over. And so looking at a picture of a decreasing continuous function, supposing this is n and this is n plus 1, if I make a rectangle like we did when we proved the theorem, the area of that box, because its width is 1, the area of that box will be the same value as the a sub n plus first term. And the next point would be n plus 2, and the area of that box would be a sub n plus 2. And from the picture, it's pretty easy to see that r sub n is less than or equal to the integral from n to infinity of f of x dx. Because the value of the integral from n to infinity, that's that area under that curve, and because we're using right endpoints on that interval, the value of the integral is greater than the value of the sums of those boxes. Now let's figure out if we can find something that is less than the remainder. So draw a similar picture. So we have n, and then n plus 1, and n plus 2. So if I find the area of these boxes, so that's a sub n plus 1, then I plug in the left endpoint, this box would have area a sub n plus 2, so a sub n plus 1 plus a sub n plus 2, which is the same thing as r sub n. is greater than or equal to, see the integral there would begin at n plus 1. So the integral from n plus 1 to infinity of f of x dx. So what that tells us is that our remainder r sub n is smaller than the integral from n to infinity, but bigger than or equal to the integral from n plus 1 to infinity. So if I wanted to figure out the possible error or the remainder in the first 100 terms, it'd be less than the integral from 100 to infinity of f of x, and bigger than the integral from 101 to infinity of f of x dx. So that is summarized in the following slide. So supposing that you have f of k equals a to the k, so f of 1 gives you the first term, f of 2 gives you the second term, etc., and f is a continuous positive decreasing function for x bigger than some n, and your sum is convergent, then if r sub n, the remainder, is the sum minus the partial sum, you have that this remainder is bounded between these two integrals. So let's approximate the sum of the series from n equals 1 to infinity of 1 over n cubed by using the sum of the first 10 terms, and then let's find the error involved in this approximation. So the sum from n equals 1 to infinity of 1 over n cubed is about equal to the 10th partial sum, which is the same thing as a sum from n equals 1 to 10 of 1 over n cubed. So what that really is we have 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed, all the way up to 1 over 10 cubed. And please use some kind of calculator to figure this out. That's approximately 1.1975. Now the question is how accurate is that? Like, is that accurate enough that we're not going to notice some kind of error due to leaving off the terms from 11 to infinity? And we can use the theorem above. It tells us the remainder of using 10 terms is less than or equal to the integral from 10 to infinity of 1 over x cubed. So that's the same thing as finding the limit as b goes to infinity, the integral from 10 to b, x to the negative 3 dx. So the limit as b goes to infinity, antiderivative of x to the negative 3 is x to the negative 2 over negative 2, evaluated from 10 to b. So we'll have the limit as b goes to infinity of negative 1 over 2b squared plus 1 over 2 times 10 squared. So the negative 1 over 2b squared goes to 0. We'll have 1 over 200. Same thing as 0.005. So the error is less than or equal to 0.005. Now, next, suppose you needed to have an answer that was accurate within 0.0005. So what you need is you need an n where r sub n is less than or equal to 0.0005. So obviously more than 10, because in the previous example we had that summing the first 10 terms had an error of at most 0.005. So we know that r sub n is less than or equal to the integral from n to infinity of 1 over x cubed dx. So there's a lot of letters, but that's the same thing as the limit as b goes to infinity, integral from n to b, x to the negative 3 dx. So the limit b goes to infinity, and to differentiate, we get negative 1 over 2x squared again, from n to b. Or we have the limit as b goes to infinity of negative 1 over 2b squared plus 1 over 2n squared. And since b goes to infinity, this term goes to 0, and our r sub n is less than or equal to 1 over 2n squared. So what we have to have now is this 1 over 2n squared needs to be less than 0.0005. So now we just need to solve that inequality. So multiply both sides by 2n squared, and we'll have 1 is less than 0.001 n squared. Divide by 0.001, and because that 0.001 is positive, the inequality does not flip, so we'll have 1,000 is less than n squared. Now root both parts of the inequality, and we'll have root 1,000 less than n. And so we have that n must be greater than 31.6227. So using 31 terms isn't going to be good enough, but as long as we have that n is bigger than 32, or equal to 32, that will ensure the accuracy that we need. So let's try another one of those. Let's approximate the sum from n equals 1 to infinity of e to the negative n using the sum of the first 4 terms, and then include an estimate of the maximum error in your approximation. So the sum from n equals 1 to infinity of e to the negative n will be about equal to the 4th partial sum. So the sum from n equals 1 to 4 of e to the negative n. So that's adding e to the negative 1 plus e to the negative 2 to e to the negative 4, and that's about equal to 0.5713. So there's the estimate using the first 4 terms. Now the error, which is going to be r sub 4, is less than or equal to the integral from 4 to infinity of e to the negative x dx. And that's the same thing as the limit as b goes to infinity, integral from 4 to b e to the negative x dx, or the limit as b goes to infinity, negative e to the negative x, evaluated from 4 to b. This is the limit as b goes to infinity, negative 1 over e to the b plus 1 over e to the 4. And since b goes to infinity, the 1 over e to the b goes to 0. So this limit is just equal to 1 over e to the 4th, which is approximated by 0.0183. So the error is less than or equal to 0.0183. Not so bad for only summing 4 terms. Alright, a final example, we're going to find capital N such that the remainder, or the error, is less than 0.001 for this convergent series. So from our previous theorem, we know that r sub n is less than or equal to an integral from capital N to infinity, 1 over x squared plus 1 dx. So we can find that integral using a limit as b goes to infinity, n to b, 1 over x squared plus 1 dx. And an antiderivative of 1 over x squared plus 1 is arctangent. So limit as b goes to infinity, arctan x, evaluated from n to b. So you have the limit as b goes to infinity, arctan b minus arctan n. And as b goes to infinity, arctan of b goes to pi halves. So r sub n is less than or equal to pi halves minus arctan n. And now what we're going to need is we need pi halves minus arctan of n to be less than or equal to 0.001. So first I'm going to take away pi halves, so negative arctan of n is less than or equal to 0.001 minus pi halves. Divide by negative 1 and flip the inequality. Arctan of n will be bigger than or equal to positive pi halves minus 0.001. And now we'll have to apply tangent to both sides. N will be bigger than or equal to tangent of pi halves minus 0.001. And before you evaluate this with a calculator, make sure your calculator is actually in radians and not degrees. And you'll find that n must be bigger than or equal to 999.9997. So since you need more than 999 terms, you will have an error of less than 0.001 so long as n is bigger than or equal to 1,000.